Hi, this is section 10.3. It's about simplifying radical expressions. Remember, radical expressions are expressions involving roots, square roots, or other kinds of roots. And in this section, to simplify things, we're just going to assume that anytime we use a variable, it represents a positive number instead of a negative number. That makes things easier because then we don't have to worry about what if we're taking the square root of a negative number, or what if we start with a negative number and square it and then take the square root, and so we end up with the absolute value of what we started with. So to avoid dealing with all that, we're just going to assume that all the variables represent positive numbers. Okay? Now, what we're going to be doing in this section is based on the rules for multiplication and division with radicals. The product rule that says that if you multiply two roots together, it's the same as the root of the product. So square root of a times square root of b equals the square root of a times b, and it still works for other kinds of roots, and it works for division. The root of something divided by the root of something else equals the root of the something divided by the something else. So with multiplication and division, you can interchange the order of the multiplication or division and the roots. When it comes to addition and subtraction, which we'll talk about later another day, it does matter what order you do things in, but with multiplication and division, it does not matter. You can interchange the order. So some examples. The square root of 5 times the square root of 11 equals the square root of 55. 5 times 11 is 55, so the square root of 5 times the square root of 11 equals the square root of 55. The cube root of 3 times the cube root of 7 equals the cube root of 21. 3 times 7 is 21, so the cube root of 3 times the cube root of 7 equals the cube root of 21. The square root of 5x times the square root of 5y equals the square root of 25xy. 5 times 5 times x times y. And here we can do something more, because we can break this up into the square root of 25, which is 5, times the square root of xy. So we can leave it as just 5 times the square root of xy. Now some examples with the quotient rule. The square root of 10 over 81 is equal to the square root of 10 over the square root of 81. And we can go a little further with that because the square root of 81 is 9, so we can write this as the square root of 10 over 9. The square root of 9c to the 8th over 100 would be the square root of 9c to the 8th power over the square root of 100. And then the square root of 9 is 3. The square root of c to the 8th power is c to the 4 power. And the square root of 100 is 10. So we end up with 3c to the 4th power over 10. Now, remember which numbers are perfect squares. Those are the numbers that we can take the square root of and just get a nice whole number answer. Like, because 5 squared is 25, that means whenever you see the square root of 25, you can say, oh, that's just 5. And with expressions, x to the 5 squared is x to the 10 power. So whenever you see the square root of x to the 10 power, you can say, oh, that's just x to the 5 power. So the square root of something that is a perfect square, we can just right away simplify to what the square root is. But what if we have the square root of something that isn't a perfect square, something that's not on this list? Sometimes we can still, even if we can't just say what the square root is as a nice whole number or something, sometimes we can still simplify it. So now we're going to talk about how that works. Let's say we want to simplify the square root of 90. Now, if you ask your calculator what the square root of 90 is, it's going to give you something like 9.48683 and so on, which is not what we mean by simplifying. When you take the square root of something that is not a perfect square, so it's not just a nice whole number or a simple fraction, it's something that is irrational, so it's got a decimal version where the digits just keep on going forever. So that's not what we want when we are trying to simplify something like this. Because if you stop writing anywhere, then what you've got is not exactly the square root of 90. You have to write infinitely many digits before what you have is exactly the square root of 90. So 90 is not a perfect square, but we can factor it or break it up into 9 times 10. And then the square root of 90 would be the square root of 9 times the square root of 10. And we can do something with the square root of 9. 9 is a perfect square, so the square root of 9 is 3. And then the square root of 10 isn't anything special, so it has to stay just the square root of 10. So we can simplify the square root of 90 into 3 times the square root of 10. So it still involves the square root of something, but that something is smaller and simpler than the radicand that we started with. So to simplify, we want to get as much as possible out from under the radical sign. Here's another example, the square root of 50. 50 is not a perfect square. We could break it up into 5 times 10, but that wouldn't really help because neither 5 nor 10 is a perfect square. But another thing we can do is we can take 50 and break it up into 25 times 2, and that does help because 25 is a perfect square. When you got the square root of 25 times the square root of 2, we can say what the square root of 25 is. It's 5. So we end up with 5 times the square root of 2. What about the square root of x to the 7th power? Now, x to the 7th power is not a perfect square. It's not something that we can take the square root of and just get a nice whole x to some power. But what we can do is factor it into x to the 6th times x. So it's x times x times x times x times x times x times x. And we can take the square root of x to the 6th and get x to the 3rd power. And then we still have the square root of x that we can't do anything more with. We'll have to just leave that part as the square root of x. So the square root of x to the 7th simplifies to x to the 3rd times the square root of x. We got most of the x's out from under the square root sign, but there was still one left over underneath the radical sign. And another way to look at what's going on here is that x to the 7th is x times x times x times x times x times x times x. The ones that we could pair up, where we have the square root of x times x, every time we have the square root of x times x, that's just x. And then we have one leftover x under the square root sign. So it is x times x times x, that is x to the 3rd power, times the square root of x. What about the square root of w to the 11th power? What can we break up w to the 11th power into? What's the biggest perfect square that we can factor out? Answer, we can break it up into w to the 10th power times one more w to the 1st power. And then we have the square root of w to the 10th power, which is w to the 5 power, times the square root of w, which has to stay just the square root of w. Now let's do one where we're mixing numbers and variables. the square root of 50x to the 8th. So for the 50, we break it up into 25 times 2. For the x to the 8th, that already is a perfect square. We can go ahead and say what the square root of x to the 8th is. So when we break it up into the individual square roots, we have the square root of 25, which is 5. We have the square root of x to the 8, which is x to the 4 power. And we have the square root of 2, which has to stay just the square root of 2. So we end up with 5 x to the 4th times the square root of 2. Another example, square root of 36w to the 11 power. Okay, 36 is already a perfect square. We don't have to break that up. W to the 11th power is not a perfect square, but the biggest perfect square we can factor out is w to the 10th. So we can break that up into w to the 10th times w. And then when we take the square root of each individual factor, the square root of 36 is 6. The square root of w to the 10th is w to the 5th power, and the square root of w just has to stay the square root of w. So our final answer is 6w to the 5th times the square root of w. And now let's do one with a cube root. The cube root of 40. 40 is not a perfect cube, so the cube root of 40 is not just a nice whole number. But can we take 40 and break it up into one factor that is a perfect cube times something else that isn't? Answer, we can break 40 up into 8 times 5. So the cube root of 40 would be the cube root of 8 times 5. So we've got the cube root of 8, which is 2, times the cube root of 5, which has to stay just the cube root of 5. So 2 times the cube root of 5. What about the cube root of 27 x to the 6th y? So we have the cube root of 27, which is 3, times the cube root of x to the 6th power, which is x to the 2nd power, x squared, times the cube root of y, which we can't do anything with. We have to just leave it as the cube root of y. So this simplifies to 3x squared times the cube root of y. What about the square root of 13b to the 16th power? So the square root of 13, we can't do anything with that. 13 is not a perfect square, and we can't factor it so that one of the factors is a perfect square. So it has to stay just the square root of 13. But the square root of b to the 16 power is b to the 8 power. So we got the square root of b to the 16, which is b to the 8, times the square root of 13, which has to stay the square root of 13. Okay, I'm going to end this video here and come back in part 2 to do a few other things. See you then.